Good evening, everyone. Welcome to the Bell's October virtual star party. And it is just now 8 o'clock, so people are joining us. We're happy to all see you or see your names here logging in. We'll give it a few more moments to let more people have a chance to get in. And just so you all know, we are recording this. And we welcome questions from you guys. It's one of the favorite parts of our jobs here at the museum is to learn about what you're interested in and what questions that you have. So throughout the time here, feel free to use the Q&A box to ask us any questions that you may have. Okay, and so we have a few people here working at the Bell Museum. I am Sarah. I am the Planetarium Programs Coordinator here at the museum. Up on the roof deck tonight, hoping that the clouds go away. And just in case they are, we did set up a telescope. We have Tad LaCorsia, our planetarium educator. And we have Megan Meacham, who is one of our student staff here at the planetarium. We also have a few of our other Bell staff behind the scenes here tonight, helping to answer questions and things like that as they pop up through the evening. And so you might see a few of their names behind the scenes like Libby, Laura, Amber, or Ramona. So any one of us will be happy to answer questions along the way, but we'll use the Q&A box to address any of your questions as they come in here. And it is cloudy, unfortunately. For a brief window of time, we thought this morning that the clouds were predicted to depart just in time for tonight's event. But alas, the clouds stuck around. But we haven't totally given up hope. Tad is up on the roof deck right now, working with the telescope. So Tad, if you want to show us a brief moment of what we have set up just in case the clouds go away, we'd love to see what you have going on up there.
Sure. Thank you. I'm sorry, I'm out of camera. I'm using a different camera here, so I'm a little off center. So hi, everyone. I'm Tad. I'm up on our observation deck, John Ruth's observation deck. It's very cold. I hope you're all inside where it's warm, because you're smart. I'm up here with another, I think, smart person, but she is out here tonight. Want to say hi?
Hello, my name is Megan. I'm a student at the U of M. I hope you guys are all nice and warm.
What are you studying here, dude?
I'm studying aerospace engineering.
So if you want to put a telescope up into space where you don't get clouds, talk to Megan.
Yep.
I guess they can't actually see me doing that, but all right. Our telescope is set up right behind me here. Get out of the frame there. This is a Stellaview 130 millimeter refractor. It's got a ZO 183 monochrome camera on the back of it. It's a little fuzzy there, camera's out of focus. You can see the clouds as well in the background. Oh, so many clouds in the sky. So right now we're pointed at roughly where the moon is, would be if we could see anything right now, but we can't even see that, unfortunately. But this is a great scope for something like the moon, for something like planets. Refractors tend to have very crisp views. And with something like the moon and a black and white camera, well, the moon is more or less black and white, so we can get a lot of great detail with a 5-inch 130 millimeter scope. We get a lot of detail on that. Can see some magnificent craters. Sarah, I don't know if maybe, I don't want to jump the gun here, but I know we had a picture we took a while ago with this camera. Do you know if we can share that?
Yes. So I will go ahead and share my screen again here. And we actually used that particular scope and camera setup just last week before all the clouds came in of this week. And we didn't image our moon. I'll skip a few slides here, but we imaged Jupiter and its moons. And so when you go outside right after sunset, you might be looking in the south and see two very bright points of light. And so I'm going to go back a moment here and show our star map, because you can download our star map from the Bell Museum's website, or if you happen to visit here at the museum, you can grab one in person. And in the middle of each star map, each pamphlet, we have the actual map of the sky. And so looking at our October star map here, if we look towards the south, kind of the lower edge of the map, we see Jupiter and Saturn in those orange hexagons. And so Jupiter and Saturn are two of the planets we can see with our naked eye. So we don't need a pair of binoculars, we don't need a telescope. And so Jupiter's gonna be the brighter of these two because it's a little bit larger and it's a little bit closer. So that's what we pointed our scope at last week here. And so what we actually saw was Jupiter, that really bright sphere there in the middle, was overexposed in this camera because it's so bright that the camera that we put on the back of that scope Tad just showed us, we couldn't quite see the bands of clouds through this particular setup. But what's great about this is that by overexposing Jupiter, which reflects a lot of the sunlight, we can see three really kind of smaller dots just off to the left here in this image. And these are actually three of Jupiter's Galilean moons. And so these are some of the moons that Galileo saw back in 1610. So the very first observational evidence that the Earth was not the center of the solar system. And what's really cool about it is that these moons, you see three of the four because they all orbit Jupiter at different rates. For instance, the one closest to Jupiter in this image with the green arrow and the E above it, that is the moon Europa. And so Europa here orbits Jupiter once about every 3.5 Earth days. Callisto, which is the orange arrow with the C on it, Callisto orbits Jupiter about once every just a little about 16.5 Earth days. And then Ganymede, this third one in pink or with the G here, orbits Jupiter about every 7 Earth days. And so when we took this picture last week, Io, that fourth moon of Jupiter, which orbits the planet about once every day and a half, a little over every day and a half, was actually right in front of Jupiter when we took this image. So we couldn't see it because Jupiter was overpowering any light that Europa would have, or that Io would have reflected. What's great about this is because these moons orbit so quickly around Jupiter, is that if you go out every few hours or even look from one night to the next night, you can actually see they'll be in slightly different locations. And that's what Galileo saw when he first looked at Jupiter and its moons here. Actually, in fact, with Io going so quickly around Jupiter, you can actually track its movement and as it moves across Jupiter here. And you could probably see something that different about every half an hour or so, maybe every 30 to 60 minutes. You can actually track the movement. That's how quickly Io orbits Jupiter here. And so this is a really cool image that we took just last week, and that will kind of start to document some of these images too. So over time, we here at the museum, we could possibly even create our own record of the orbits of these moons going around Jupiter. But if you have any questions, if you just joined us, please feel free to put them in the question and answer box here. We love questions, are my favorite part of the day. And one of the questions that came in is that next week is a full moon on Halloween. And so right now we're at about that first quarter phase. And October here was actually a really interesting month, that this month we had a blue moon for our own moon. Now, once in a blue moon, if you've ever heard that saying, actually has some basis in astronomy, because we started the month with a full moon on October 1st, and we're going to end the moon with a full moon, or end the month with a full moon as well. And so whenever there's 2 full moons in one calendar month, that's when we say it's a blue moon. And I don't know if the last time that this happened on Halloween was actually in 1944, but that question was asked by Karen. Yes, it's going to be the first blue moon here in a long time, and it's really kind of cool that it happens to be on Halloween this year. Yes. But a few other questions came in about moons here. Why does Jupiter have 3 moons? It doesn't. It has almost, I think last time I checked, 79 moons. But these 3 that we see on the screen that we took a picture of last week, these are 3 of the Galilean moons. So these are some of the largest, and because they're the largest, they reflect the sunlight back to Earth the best. And so we could see them with even just a pair of like a backyard telescope. We don't need anything high tech. Galileo sure didn't back in 1610. And so these are just the largest ones. In fact, Ganymede here is actually the largest moon in our entire solar system. It is actually larger than Mercury itself. So the moon is actually larger than the planet. So it is quite spectacular sight, and they each have their own personalities. So another one was, how many moons does Saturn have? Saturn actually just overtook Jupiter in the most moon counts. So in summer of 2019, we discovered 20 new moons of Saturn. And so Saturn is now, I believe, at 82 or 83 known moons. And so they are our gas giants, and so they have the strongest gravity of any of our planets here in our solar system, and they were able to capture and hold on to many of those moons. Here we just see 3 of the Galilean moons just from our telescopes up on the roof deck. Okay, so we have lots of questions coming in, and I love it. What did Galileo think he saw, and why did that lead him to his idea that Earth is not the center of the universe? That's a great question. The idea that the Earth was the center is because when we look up in the sky, we see the sun and moon rise in the east and they set in the west, and the stars do. So just visually, it appeared obvious to everyone that the Earth was the center. Everything moved around us because that's what the sun did every single day. And therefore, the moon did as well, because if the Earth moved, we'd leave the moon behind, is what they thought, is that the moon wouldn't be able to follow the Earth with it if the Earth, in fact, moved. So it was a complicated system because they thought if Earth could move, then how would it hold on to the moon? And then, so therefore, we know the moon didn't go anywhere and we had to be the center. This here, when we saw, when Galileo saw these 3 moons and then Io during some of his other observations, these Galilean moons, proved that a planet that we knew orbited the Earth, we knew it moved, but we at the time thought it orbited Earth, a planet out there that we knew moved could still hang on to its moons. We didn't know how yet, but the fact that we had observational evidence that a planet had moons that could, and it hung on to them as it moved across our sky, kind of put into question, well, maybe Earth could move too, and maybe the idea that if Earth moved, we'd lose our moon was not valid. And so that was one of the observations that started really putting into question some of those things we just thought were true, because they just looked obvious that the sun and moon rose in the east and set in the west, and we had to be the center. So that's why making observations and going where the observations lead you, and if that's more questions, that's great, that's more questions, versus just assuming something and then calling it done, because nothing in science is ever just done. And so I think it's a really cool story of what he saw back in 1610, and we can see here and be a part of that. Okay, so what is the dot in the upper right of the image here? So this image, it did capture some stars as well. And so the night we were up there, we saw some stars in the background. So I don't believe that is one of Jupiter's moons up there in the upper right of the image, but that was probably one of the stars that also happened to be in that area of the sky. Yep. Is Jupiter's axis upside down? This question comes from Sophia. No, Jupiter's axis is roughly the same orientation as the Earth. So all planets have their axis, their north and south pole, and they rotate. The only 2 that are different from Earth, or are a lot different from Earth, are Venus, which actually rotates almost completely opposite. So it's almost flipped over 180 degrees. And so it rotates backwards, where the sun would rise in the west and set in the east compared to us. And the other exception to that is also Uranus, which is almost tipped over sideways. But all the other planets have roughly the same orientation as Earth, with north pointing up, even though there is no up in space, but pointing in the same kind of direction that Earth is. So all the other planets, kind of the sun would rise in the east and set in the west there. Okay, so looks like a few of you noticed that star up in the upper right. Yep, that was just, as far as I could tell, a star there. None of the other moons are typically bright enough for us to capture, but you could potentially see them with a strong pair of binoculars and just definitely a backyard telescope. Are gas giants, this question comes from Peter, are gas giants failed stars? Some people could probably try to make that argument, but I think they're different enough that they're not really failed stars. In order to be a failed star, I think Jupiter would have had to be 8 times its size to actually become a failed star. So its formation process is very similar to stars, But because the sun formed first and the sun gobbled up about 99% of all the material that was in this area that could have made things, there just wasn't enough material left for Jupiter to become a star, because then it also made, the solar system had all the other planets that formed, and there are asteroids and our comets. So some people like to make the argument that Jupiter could be a failed star. I just don't think there's enough evidence to show that Jupiter was big enough to actually have been a contender to be a star. Yep. Oh, the moons here each have their own personality. Great question. Thank you for asking it. Io, which we can't see here in this image because at the time we took it is right in front of Jupiter, kind of right there. Io's playing this game of tug of war with Jupiter, and this tug of war is stretching and squeezing the moon. And so Io is actually very, very volcanic. And so if you look at images from Io, it almost looks like a moldy, cheesy pizza. So sometimes we nickname it the cheesy or pizza moon. Because a lot of those volcanic activity has sulfur, and so it leaves spots all over it. So it's a very, very volcanic area moon. It actually, every time we've looked at it with a spacecraft, there's an eruption happening somewhere. So that is that personality, if you will, of that moon. It's very volcanic. Europa here, the E, is a very icy moon, where it does still play kind of a tug of war with Jupiter, but instead of having volcanic activity, it has geysers. It's a little bit further away than Io, and it's covered in ice. But that stretching and squeezing of Europa, that tug of war that's playing with Jupiter, on the inside of the moon is melting that ice. And so instead of lava, there's a warm liquid ocean underneath it here. Okay, yep. So here is a picture of Europa. We can see that icy surface here with some of those cracks across it. So as Jupiter stretches and squeezes it, that ice, much like ice in Minnesota in the lakes, sometimes cracks and refreezes, and then there's the water underneath it. That's essentially what's happening here on Europa. It's a very icy moon with a liquid ocean water underneath. But you get further out from Jupiter, we get to Ganymede and Callisto, and they are icy and there's rock there, and so they just get colder and colder. And so I think it's Callisto, the farthest one out, actually has some of the oldest surface in our solar system. And so it's kind of a time capsule of what happened, because it hasn't resurfaced itself. It's not volcanic. It didn't erase the craters. And so it has kind of tells a story of the past 4.5 billion years. And so then here is an image of Callisto there, and all the kind of pockmarked craters all over the surface. So that's what I meant by each moon has a different personality, is that their physical environment is very different, even though they are for the largest moons of Jupiter, and that we can see from here. We've known for quite some time about them, but their environments are very, very different and very, very interesting. Why can't we see the other 60 plus moons? Well, a lot of these out beyond Jupiter, or out beyond these four here, are really small. And some of them are captured asteroids. And some of them can be very far away from the planet itself. And so we actually had to go there with a few of our spacecraft to detect some of those other smaller natural satellites, which we call moons. And so we can't see them all just with a backyard telescope, but we have found them with spacecraft studying Jupiter. I'm going down, could people live on Europa? Probably not the surface of Europa, because it is very icy. But there's an idea that underneath that ice, just like Minnesota, the lakes freeze over in the wintertime, maybe underneath that ice layer, maybe there's life under there. Who knows if it'll be similar to lakes here in Minnesota or not, but the idea that all the components necessary for life, it has an energy source, that stretching and squeezing, that kind of tug of war with Jupiter is providing energy to the moon. It has a protective layer, so that outer layer of ice is a protective layer on the moon, so it can protect it from some radiation coming from the sun or incoming space rocks. And it has liquid water, and liquid water is the one thing we know that all life on Earth needs. And so Europa maybe could host some type of life. We haven't detected any yet, but that is one of our upcoming missions that NASA is planning, to see if we could get there, and then what it would take to drill through that ice, a very large ice auger, to take a sample, and if anything could live there. Yep.
So Sarah,
Yes.
if I can jump in here.
Yep. Tad's jumping in with us. Thanks.
I will try to get it on camera here. It's still cloudy, by the way, folks. If you're wondering what the sky is like, if you're safely and warm inside, it's don't be outside. Well, I want to, because you're talking about ice here and water. This is a picture of our moon. This is from our camera here at the museum. This is one of the very first pictures we took when we were trying out our camera. So it's not a great picture. It's a little overexposed. Megan, do you mind holding the camera here? Sorry. All right. So it's a little overexposed. You can see a lot of those craters though. But I want to jump in because I wanted to share the picture, but also on Monday, NASA has a very large announcement set for the moon. The very large press announcement. They've discovered something very cool on the moon, at the moon, around the moon. Who knows? But that's set for Monday. I'm going to spoil things. It's not aliens. Sorry, just that's the way it goes, folks. We
can hope, though. We can wish one day.
I mean, fingers crossed. But the rumor mill has it probably. I mean, the most likely thing that they've discovered, because we just keep finding it everywhere, is water. There's some rumors out there that maybe they've discovered large deposits of frozen water underneath the surface. Some of the bigger rumors are even something like an underground deposit of liquid water, some type of very slushy water, a lot of salt in it to keep it semi-liquid. That seems to me the most likely idea, though, the presence, some greater presence of water, especially as we look forward in the next few decades, as we think about sending people to the moon. Water is this essential component. As you're saying, we need water to support human life. So with our plans to go back to the moon for good, the more water that we find there, the better. It'll help support human colonies far into the future. So anyway, Monday, big announcement. No one knows what it really is. Not aliens. Sorry again. Hashtag not sorry. But keep your eyes peeled for that.
Okay. Well, thanks for letting us know about that, Tad. Because yes, water is the one thing we know that all life in our solar system needs in order to exist. Now, we can see Jupiter. I'll reshare my screen here with our star map. Again, if you have your star map, go ahead and take a look at it. But Jupiter is just one of the 3 planets we can see right now in the evenings with our eyes. So you do not need a telescope or binoculars to see Jupiter. So we see down at the bottom part of our image here, we have Jupiter and Saturn in the southern sky. But over in the east, in the constellation of Pisces right now, we have Mars. And so you can see these 3 planets right after sunset. And one of the cool things is here is Mars, again from last week through our telescopes. And you notice here, just from, again, our telescopes here at the Bell Museum, that you can start to see some details here on the planet. Yes, it's reddish, and even without a telescope, if you look outside in the sky, it does have that kind of reddish hint to it, that reddish hue to it. So you can see that planet in the eastern sky has a little red dot. But using binoculars, or in this case, our telescopes, we start to see some things going across the surface here. And so if we kind of annotate this a little bit, that kind of dark, kind of a darker brown that went across what to us right now looks like the equator, is the Amazonian platinum. And again, I am terrible at pronunciation, so please don't hold me to that pronunciation. But then we also see Hellas Basin and some impact areas here. And as Mars, just a few days ago, was at its closest approach, or its opposition to the sun, which means it was completely opposite Earth from the sun. So the sun is on one side of the Earth, Mars is on the opposite side. And it was actually in part of some of its closest approach. This past summer, we had what's called a launch window. And so when it made sense to launch things from Earth to Mars because of the way the planets were in their orbits, it was a shorter distance, and that the Earth kind of catches up to Mars about every 2 Earth years. And so here is, we can see some of that detail that when Mars is farthest away from Earth, we don't always get to see. And some of the other images, if you look out a few days after this, we did not take a picture of it, unfortunately, is some of our friends here have been able to capture the southern ice cap of Mars. So there is actually still water on Mars. Most of it's frozen in the permafrost and in the ice caps. But the ice caps aren't just water ice. Some of it has carbon dioxide or dry ice as well. And so that key for life, that search for water, is something that's carrying us from the moon to asteroids. If you were paying attention this past week, we landed and captured some material from the asteroid Bennu to Mars here, which again is where we're hoping to send humans by the decade of the 2030s. That search for water is a key one. And we can see some of these details here on Mars that give hope to that water was once on the surface of Mars. In fact, the whole surface here is rusted because in the past it had more oxygen in water, so that iron in the surface of Mars was able to rust. That's what gives it that kind of reddish hue here. So the search for water is definitely a key one. So there was a question here, what is the planet in the eastern sky around midnight for August and September? So that would have been Mars here. So in the eastern sky around midnight, we saw Mars. And as the year is going on, Mars is rising a little bit earlier and earlier each evening. Now, if you're not a late owl, or in this case, the sun hasn't been setting too late, if you're a really early bird, you can see a fourth planet in our sky, which is Venus, which rises just before sunrise, around 4:30 in the morning. I am not an early bird, so I'm going to wait for that one to make its loop around the sun and be up in the evening sky here in a few more months. But you can see these planets are going to be nice and bright. They will be different from stars because they'll be nice and bright, but they will not twinkle. That's how you know you're looking at a planet and not a star. Oh, here's a fun question. What would a saxophone sound like on Jupiter? Well, we were just looking at Jupiter, and sound travels differently through different materials. So here on Earth, our atmosphere is mostly nitrogen, and there's some oxygen in it. That's what allows us to breathe. On Jupiter, or even here on Mars that we're looking at, their atmospheres are very different. Here on Mars, the atmosphere is mostly carbon dioxide, and so sound waves would travel differently through that gas. I'm not quite sure what a saxophone would actually sound like traveling through different material, a different atmosphere of a planet, but that could be a fun thing to test because NASA has built its rovers like Curiosity, and it sings happy birthday to itself every year on its anniversary of landing. And so I don't know if we've ever recorded what it sounds like on Mars versus what we thought it sounded like on Earth before we launched it there. But that's kind of a fun idea or a thought experiment of what would an instrument sound like in different atmospheres. I like that one. I don't have an answer to that, but I like that question. Good question. Yes, I did say Mars was rusty. That's what gives it its red color. We can see Olympus Mons, just not in this picture. We don't think, based on the detail here we were able to capture through our camera and our telescopes, it wasn't quite rotated to where Olympus Mons was facing the Earth when we captured this image here last week. But I have seen pictures of Mars taken from Earth-based telescopes that you can see Olympus Mons, just not in this one. Maybe we'll be lucky enough to capture it here as Mars stays in our fall sky for the next few months. Okay, but there's something else really interesting about this picture of Mars. You may have seen it, but I'm going to zoom in a little bit more. I'm going to make the picture larger. And it's not the features here, although we can see what I'm trying to get at here a little bit better in this picture. But if you look at kind of this bottom right corner of Mars, it looks a little bit more red. But if you look up the top left kind of edge of Mars, it looks a bit more blue. Now, that's not because Mars is more red in one area of it and more blue on the other side of it. That's actually a feature of our telescope. So here at the museum, we have both reflectors, which are telescopes that use mirrors, but we also have refractors, like the one that Tad had set up. And that's the one that we took this picture through last week. And so refractors use lenses instead of mirrors. So like the lenses of binoculars or your reading glass lenses. Now, as light passes through lenses, whether it be a telescope or binoculars or a prism here, light bends, and different colors bend at different amounts. So we look at the prism on the right side of this picture. When light goes through a prism or a piece of glass, like the lenses in a telescope, the red light, you can see here, doesn't bend as much as the blue and the purple. And so because red light doesn't bend as much, that's why when you look at that picture of Mars here, red didn't bend as much, so one side looks red and the other side looks blue. And so it's called a color aberration, and that only happens when light passes through lenses. And so different types of telescopes actually really do some interesting things. You don't get this color aberration with reflectors, with mirrored telescopes, but that doesn't mean telescopes that use mirrors are better than telescopes that use lenses, because the one we took this picture through is really, really good with taking planetary images, and is really good at looking at things here in our own solar system. And so we use our different telescopes here at the museum for looking at different targets in our sky. And this is just a really cool feature that we can see here only through our refractors, is that color aberration with the red on one side and kind of blue on the other side. The same thing is why we have rainbows in the order we have. Red is always that top part of a rainbow. The blue or purple is always that inner kind of arc of the rainbow, because red light does not bend as much as blue light does. And rainbows are caused when light passes through water droplets in our atmosphere. And so I thought this image here of Mars was not only interesting because of Mars itself, but because of some of the things that our telescope can do to that light passing through it. It's a really cool feature, I think, of the equipment itself. So we are still looking at Mars here, and there's a question: has liquid water been found on Mars? Maybe. Because during some of the warmer months on Mars, because Mars has seasons just like Earth does, that some of that water ice will actually melt and go down the sides of some craters. But we've also, that would be like sublimation, when it goes from ice right into a gas form. But that could hint at maybe some of it passing through a liquid state. We think about a year or so ago, we thought that maybe we found an underground liquid lake on Mars, but it would have been really, 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 really salty in order to still be liquid here on Mars. And so we have found things that hint that there could still possibly pockets of liquid water, again, very, very salty, but nothing's been confirmed like, oh, look, there's a giant lake of water on Mars. So we know water's there, just the ones that we are certain about is still in its frozen form. And let's see, do you think it'd be realistic to making a shelter on Mars that humans could live on? Would it be realistic? We're hoping to. To live on Mars, I've heard some scientists say that it would actually be easier to live in like the Sahara Desert, because we're already on Earth and there's some things we wouldn't have to worry about, like breathing our atmosphere. But we're still hoping to send humans to Mars because there's some things that robots just can't do for us. You know, as great as our orbiters are, and as great as our landers and our rovers are, there's some things that we're really hoping that humans can go and do that our rovers and our orbiters and our landers just cannot for us. So while it's going to be extremely difficult, it's still a goal that we have. So hopefully one day within our lifetimes, we will see humans on Mars. Okay. So I saw a question here at the bottom. Does that mean there's life on the moon? Because we've been talking about kind of that thread of finding water in all these places. We don't think there's any life on our own moon. So I don't think we're even holding out hope for that. Maybe one day it'll surprise us. But what we did just this past week is collect samples from an asteroid, Bennu, and we're hoping to find evidence or some clues as to how life maybe existed or what the solar system was like back at the very early stages. And that could maybe give us a hint to how life evolved from the solar system back, 4.5 billion years ago. Okay, there's some other really cool things. We can always come back to planets. Planets are awesome things to see in our sky, but I do want to show you a few other things that are up and are visible under really dark sky conditions with the eye, but usually they're best with a pair of binoculars if you can just have that. So one of them is actually in the constellation of Pegasus. So we look back at our star map here. Mars is over in our eastern sky. Pegasus is not too far away. Pegasus is this square of stars right here. kind of makes up the body of the horse. And then we see the head of the horse kind of arcing here. And then the front legs of the horse kind of coming up a little bit closer to the center of our star map. Now, if we go back to the head of the horse, the brightest star in Pegasus is this one right here. It's called Enif. And just off of that brightest star in the constellation of Pegasus is M15, which is a globular cluster. Now, last month, we looked at the globular cluster in Hercules. Now, this one was another gorgeous one that we had a chance to observe an image here. And globular clusters are just so gorgeous. I personally feel like they are, because there's so much packed in this tiny little area. And I say so much and tiny. It looks tiny to us here, but this globular cluster from edge to edge here is over 210 light years across. So this globular cluster, there's over 30,000 stars just in the core of this cluster alone, not counting any of these ones that are kind of a little bit more dispersed, a little bit further out. This cluster is larger than our whole entire solar system. From the center of our sun, from the sun at the center of our solar system all the way out to the Oort cloud, the cloud of comets that surrounds our solar system, that's about 1 light year. And so this cluster here is 210 light years across. So this is even large. This is ginormous compared to our own solar system. And what's awesome about these things is that globular clusters are really, really, really old. This one here is estimated to be about 12 billion years old. That's twice as old as the Earth itself. So these stars here formed before the sun was even around. And much like the comets and the asteroids that are kind of time capsules of how the solar system formed, these globular clusters out in space are kind of like time capsules of what the universe was like back in the very early stages. And this, again, is an object you can see with a pair of binoculars just off of Pegasus' head there. And so if you look at it in the sky, if you have a really dark sky, maybe get away from the cities, you see it like a little tiny smudge. But then again, looking through a pair of binoculars, you can start to resolve some of these stars. In a telescope here, you see that bright core, and they're gorgeous. The idea that these things are twice as old as the Earth itself just boggles my mind. That there are stars out there that are nearly as old as the entire universe. And the universe only being about 13.8 billion years old. These are estimated at 12 billion years old. Oh, yes, let's take a step back and how to read their star map, because if you are going to go outside and look for this cluster of stars, let's remind ourselves how to do that. So if you look at our star map, we have our 4 cardinal directions, north, south, east, and west. And if you look at it, east and west appear kind of backwards, because these star maps are not meant to be held while you're like looking down at the ground, because the stars are obviously above us. And so what you do is you figure out which direction you're facing. So if tonight you were outside and it wasn't cloudy, you could see Jupiter and Saturn. If you're staring at Jupiter and Saturn tonight, you'd hold south kind of towards your torso and then flip the star map above your head. And by doing that, east and west then are on the appropriate sides of the north and south there. But you might notice here that our star map here is a giant circle. That outer circle of our map is our horizon. Because if you stood in one spot and spun all the way around to look all the way around, you'd trace out a circle. So when we find something that's closer to the edge of our map here, like Mars on our map, it tells us that it's closer to the horizon. Now, in the very center of the map, near the very center, it's not at the very center, is Cygnus the Swan. So that was a constellation that was part of the Summer Triangle. That's very close to the center of our map here, and that would be the point directly above you. If you were to stand outside and look straight up, that's our zenith. So that's right above you. And so that kind of gives you an idea. If you're looking closer to the edge of our star map, you're going to be looking at something that's closer to the ground. If you're looking at something that's closer to the center of our map, you're going to be looking at an object that's kind of straight above us. So when we look for M15 in our sky tonight, it's kind of halfway. It's slightly closer to the center of our map than it is to the horizon. And so we're going to look a little up, about 45, maybe about 50 degrees above the horizon. It'll be kind of nice and easy in the middle there. Again, looking for these 4 stars that make up the Great Square of Pegasus, or the Fall Square, you might know it as. That'll give you a good hint of where to look in our sky as well. And then if you're lucky enough to be a little bit farther away from the cities, you might see this streak of gray going across our star map here, kind of from the southwest to northeast right now. That is our Milky Way galaxy. So that is not something you can see from here in the cities with your eyes, but you do need to get out far enough away from the city lights in order to see that, but it is possible to see that. So that's the basics of how you read our map here. We have our horizon at the edge, we have the zenith in the middle, and we can kind of gauge based on how close the objects are to those two locations, where to look in our sky or how high up to look in our sky. Okay, so let's go back to that globular cluster here.
Sarah, I'm just going to jump in for a second.
Yes.
So I just want to announce here, because we're up on the deck and we're waiting for the clouds to clear, and I just want to announce that we briefly saw some light that we think was the moon, and then it disappeared. So that's been your weather report from the John and Ruth Huss observation deck. Stay safe and stay warm, Minnesota.
Yes, we were hoping that it would clear up. Some of our the weather predictions earlier today gave us hope enough that but it's just not working out here. Okay, so here's a kind of a funny thing that came in. Do you think we could think of a prettier name for globular clusters? Yes, globular cluster is kind of a chunky name, if you will, but it's only one type of star cluster. We also have open clusters, which I believe is what we took a picture of next. So let's take a look at, this is a globular cluster where they're all kind of clustered together. They're very kind of blobbish or globular here, if you will, in the center. But if you take a look at this one, this is the double cluster in Perseus. And it kind of worked out for us the other night because this is just one of the two clusters in Perseus. We couldn't quite figure out which cluster this one was, but we had some trouble finding both of the clusters. This is definitely a binocular object. We think one of the things that we ran across is that we were just too kind of zoomed in or too focused in with our telescope the other night. So we only saw one of the two clusters. But if you notice, this one is different from the last one we just saw. This one isn't as tightly compact in the middle. This one's kind of a little bit more spaced out. And so this is an example of an open cluster. Now, open clusters tend to be a lot younger than globular clusters. So the M15, the globular cluster in Pegasus that we just saw, that was almost 12 billion years old. However, this one here, these open clusters in Perseus are only estimated at about 3 million years old. So that's extremely young as far as stars go. Our sun is 5 billion years old, and so these 3 million-year-old stars are very, very young. And you can see that they are definitely dispersed differently than our globular cluster that we just saw. This is again something that if you're in a dark place away from city lights, you can see these two clusters with your eyes. You don't need binoculars or telescope. You definitely need them with the light pollution here in the cities. But let's go back to our star map and find that double cluster. So we had Pegasus and M15 here. Well, Perseus, if you know Greek and Roman mythology, Pegasus, he had Pegasus as a companion in some of those myths. So let's follow Pegasus around past Andromeda here, up to the northeast corner, where we see Perseus. Perseus is marked by the very bright star Algol, which sometimes is nicknamed the demon star because it seems to like blink. And that star is one of the brighter stars in the sky. So that's why here we see that it was given kind of a different marking, kind of a starburst icon instead of just a circle. And up at the head of Perseus, if you kind of imagine his arms and his legs and his torso here, up towards the head is the double cluster that we're looking at. You can also find this double cluster by looking at the W of stars here that make up Cassiopeia. And Cassiopeia is visible all year long. And so what you do is take that center star of Cassiopeia that, it looks like a W or an M, depending on if you're a Gopher or a Badger fan. If you take that center star and kind of go out this way and draw a straight line towards Perseus' head, you will run into this double cluster of stars. And again, under a nice dark sky, you should be able to see this, see both of these open clusters with just your eyes, but definitely a pair of binoculars, and you should be able to see both of them. Yeah. How many stars are in M15? So if we compare the stars between M15, that globular cluster, which was over 30,000, to here in Perseus, this one probably has anywhere between 300 and 400 stars. And so globular clusters are much, much denser and have way more stars in them than these open clusters here that we see on the screen. Still lots of stars, 300, 400 stars is nothing to shake a stick at, but it's definitely less than the 30,000 plus stars that are in our globular clusters. Okay. What is the difference between a globular cluster and a galaxy? Great question. So galaxies have more than just stars in them. There's gas and there's planets and there's moons, and galaxies are much, much larger, like our own Milky Way galaxy here. And Tad has the clouds up on the camera, very cool. Galaxies, our own galaxy is about 100,000 light years across. And so it has these nice spiraling arms in it, which is our Milky Way. And clusters here of stars, globular clusters, even though they're old, almost as old as the universe, and in some cases can be older than the galaxies themselves. We actually think that globular clusters may be formed before galaxies completely formed, is that they're a bit smaller and they're in galaxies. But galaxies have a lot much more with them. They're clouds of gas and dust, and they just kind of behave a little bit differently. How do you estimate the age of a star? Yeah, I mean, we've been saying that these stars are anywhere from 3 billion to almost, or 3 million to almost 12 billion years old. And stars all last for, they all live for different lengths of time. And so we estimate stars and how long they live based on how hot they are and how brightly they're shining. And those are related because their temperature will help us, is related to what color they are. And then how fast they burn through their fuel also plays into how long they'll live for. And so we have a diagram, and I don't have it ready to pull up. Maybe Tad was really cool, was really quick at finding other images. Maybe he can help us out here. It's called the Hertzsprung-Russell diagram, or the HR diagram for short. And so we have so many observations of stars across the sky that we've been able to see, like, how do most of them behave? And most of them are on this line that kind of goes slanted across this graph. And that's called the main sequence. And so it's when they start to move along that line that we can kind of start estimating how old they are. Oh, here we go. Thank you, Tad. And so here is a graph of all the stars that we've observed. And so we can kind of see this from the red lower corner in the right here, all the way up, stretching up to the upper left corner when it kind of turns blue. We can measure the temperature of stars by what color they are. So that's why we have the color band across the bottom of our graph here. And we can tell how bright they are. And that's what kind of is this vertical band here. And so by comparing how bright they are, their luminosity to their temperature, we can kind of start figuring out where they lie on this kind of in comparison to all the other stars that we've been able to map. And depending on where they are on this main line here, this main sequence, we can start to see where they are in age. And if they start to kind of peel off from this line, like if we look over here kind of in the upper right a little bit, we see giants and supergiants. It kind of, those stars kind of bend away from this main line here in the middle of this main sequence. These stars here are starting to end their lives. And then way down at the lower left here, we kind of have this island of stars that are unconnected to the other two parts of the graph. And white dwarfs are actually stars that have already died. And they're just trying to they're not making any new fuel, or they're not burning any of their fuel anymore. They're just trying to get rid of any energy they have stored up. And so this is the tool that we use to estimate the ages of stars. Kind of the sun is right here. It's in the middle. It's not a bright blue star, but it's not a really cold red star either. It's kind of right in the middle. And so that's how we estimate that our sun is about 5 billion years old and has about another 5 billion years left to live. And so we kind of, over the years, we've been able to map star characteristics and figure out where they are in their lifespans. So I think of this graph here as kind of a Swiss Army knife. It can do so much here for astronomy, and there's so much information we can kind of pull and learn from it. But ages of stars is just one of those things. Okay, what would a cluster look like if viewed from its side? That is a really fun thought experiment coming from Lori here. Now, if we look at the open star cluster, I'll go ahead and switch screens again. If we look at the open star cluster here, this one in Perseus, and we go back to the one in Pegasus here, you can think of these as 3D objects. So this one here might be a little bit easier to visualize or imagine at first, because it's going to almost behave like a ball, where we have it clustered in the middle, almost spherical. And so this would be kind of seen from any angle, this one would probably look very similar, thinking it's more of a sphere. As stars aren't quite as tightly packed together in our open clusters, this is where you kind of would get slightly different perspectives. You know, maybe if we look at here, we could use these 3 kind of brighter stars in the lower left corner here, and we make a triangle with them. But if we were to get in the spaceship and travel here, this one's about 7,000 light years away, a little bit over 7,000 light years away, and we were to look at it from a different angle, those might not be the same triangle that we see from our perspective here on Earth. And so this one would probably give us a little bit more drastic of a change in our perspective if we were to travel to these clusters versus the globular clusters that are much older and much more circular or spherical. Okay. Generally, what is the star amount cutoff for galaxies? Because all these things that we are seeing so far are in our own galaxy. And I don't know that we have a cutoff, really. Because some galaxies are much smaller, and so they will not have as many stars as larger galaxies like the Milky Way or the Andromeda Galaxy, which have hundreds of billions of stars. You know, our own Milky Way is estimated to have 200 to 400 billion stars in it. You know, some of the large ones out there could have trillions of stars in them. So I don't know if there's an upper limit to a star cutoff for how big a galaxy could be. Because in about 5 billion years, the Milky Way and the Andromeda Galaxy will combine to make one even larger galaxy. And so galaxies collide all the time. So I don't know that I've ever heard of an upper limit of stars for a galaxy. Okay, how old is UY Scuti? So that was one of the largest stars that we have found. And I think that's it's kind of a yellow-orange star. So it might be in its red giant face. I'm not quite sure how old that star is, but that is one of the largest stars that we have discovered. And so with it being kind of in that yellow-orange kind of phase of its life, it is towards the end of its life. And because it is so large, very, very large stars don't live as long. And so it's kind of like I think of a very large star having to burn fuel very, very quickly to keep going, to keep shining. It's kind of like an SUV driving down the road, whereas smaller cars, they don't need as much energy, they don't need as much fuel to keep going down the road, so they won't use their fuel as quickly. And so larger stars need to use a lot of fuel very, very quickly, and they're just not going to live as long. So I'm not quite sure exactly how old VY Scuti is. But it's not going to live nearly as long as some of our smaller stars or possibly even our sun. Our sun is only 5 billion years old, and it's estimated to live for another 5 billion based on how much fuel it has left. Yep. Okay, so we are getting down to our last minutes here, and I do want to try to get to as many of these questions as I possibly can. We all greatly appreciate having you here at our virtual star parties, because we love having our star parties and our telescope nights, and we get to share all these incredible views with you. So I'm going to go through as many last questions as I can here in the last 5-ish minutes or so that we have. And I just want to say thank you all for being here, and we'll get to as many of these as we can. Where do star clusters form? Nebulas? This question comes from Pam. Stars all form in nebulas, yes. Now, where globular clusters formed and how they got here, there's still a little bit of a uncertainty about them, because there was a kind of a thought that they might be older than some of the galaxies themselves. And so you need a bunch of material out in space for stars to form. I like to think of it as like you're playing with Play-Doh. Okay, you walk into a room and you see this table. It's really very large. It has all these tiny, tiny little bits of Play-Doh in it. That's kind of like the nebula. It's just a big, huge cloud of gas and dust, kind of like the one behind me here. That's the nebula behind me is the Orion Nebula. And so you can see all those different colors. Those are different types of gases. You can see some of those bright blue stars there that are forming. And so what happens inside of a nebula for stars to form is that gravity will start pulling things together. So think of it as you walk in and you see all that Play-Doh, tiny little bits of Play-Doh all over this big, huge table. And you take two small bits of Play-Doh and you smush them together and you get a slightly larger bit of Play-Doh. Well, then you take two, slightly larger bits of Play-Doh and you smush them together and you get a medium-sized bit. And then you smush two medium-sized bits and you get a large, and then you get two larges together, make an extra large, and so on and so on. That's what happens inside these nebulas, these clouds of gas and dust just in space, is that gravity pulls that material together. And as it pulls more and more material together, it gets stronger gravity and it can pull even more material to itself. And so that's how stars are formed inside these big, huge star-forming regions and nebulas like the Orion Nebula behind me. All that gas and dust, all those different glowing colors show different elements like hydrogen or helium or oxygen. And that'll eventually get clustered together and it will form stars here. And so the stars that are formed in globular clusters like we saw in M15, or the stars in the open cluster that we saw of Perseus there, they're all going to be formed roughly the same time from that same nebula, but different nebulas are different sizes and have different materials. And so not each nebula will develop the same types or same numbers of stars across outer space.
Hey, Sarah?
Yes.
So I know I've been able to do a lot up here, except for look at the clouds. There's still clouds, by the way. Do you mind if I answer some questions?
Go for it.
Okay, because I know we just have a few minutes left. So I'm just looking at a list here. And I'm looking at one that says, Lisa's asking, what strength telescope would you need to be able to see all of the Jovian moons? To see all 89 of them, or excuse me, the 79 known ones and a bunch of hundreds of smaller ones. These days they're using things like the Hubble Space Telescope or the Keck telescopes. So the size would probably be about 30 meters, give or take, and a couple $100 million. Ken asks, where is Bennu located and can we see it? It's located in the sky, and if you have a camera and a telescope, yes. Sorry, I don't know exactly where in the sky. April, have they been able to determine if any of Saturn's moons could support life? Not exactly. Enceladus might be able to. Enceladus is a moon that has water underneath the surface, so it might be able to, but we don't know for sure. Colleen, do planets ever let go of their moons? Yes and no. There are moons that have been around the Earth, very temporary moons, we call them, that are just loosely held in the pull of the Earth's gravity, and then eventually they fly off because they're pulled by the sun usually. So it might happen. Maybe sometimes planets might lose moons that way. Sophia, is there any evidence that a planet used to have a moon that is no longer there? Sort of good follow up there. Kind of. Again, if it isn't there anymore, if we found something, we might be able to trace its path backwards and guess that it might have been around a planet, but that's kind of hard to do. It's more likely we see evidence of a moon that might be destroyed, like the rings of Saturn were probably maybe once moons that got too close and got destroyed. Can Jupiter absorb its moons and get big enough to absorb other planets? So I think we're asking here, this is from an anonymous person, could Jupiter, its gravity, pull in all these moons? Probably over enough to, like a super, super, super long time, maybe, but probably not. They have pretty stable orbits. Even if it absorbed all its moons, though, it still wouldn't have much more gravitational pull than it does now. Those moons are super small compared to Jupiter itself. Good name. Asks, is the Earth unusual in only having one moon? If so, any idea why? It is a little unusual in that way. I think this is a current area of research. I don't know if we have any exact answers why exactly we only have one versus other moons. We know it has something to do definitely with how it formed from a massive impact between the Earth and another body billions of years ago. Why we haven't gathered any other large moons probably deals as well with the formation of the solar system, that nebula that Sarah was talking about earlier. Was there a specific event or satellite? Jason's asking, was there a specific event or satellite that caused so many moons of Saturn to be discovered in such a short time? Yes. The Cassini satellite, when it arrived at Saturn in 2004, started discovering dozens of moons. We also discovered 12 a couple years ago, and that was discovered during a sky survey. astronomers were actually looking for another object beyond the orbit of Pluto. I'm sorry, this is with Jupiter. It's close enough. They were looking for another object beyond the orbit of Pluto, and Jupiter happened to be in the field of view. They knew this was a chance that they could find something, and then they did. And actually, I'm thinking that might have been Saturn again. I might have gotten that right the first time. I don't know. It's very cold up here. I'm losing brain function here quickly. And then I'm just going to scroll way down because I know there's so many questions, and I want to make sure I just answer some different ones. Oh, you know what? Here, we haven't been able to use it tonight, so this is a good question. The last one I'll go with. Terry's asking the telescope. How did we get this telescope, and are there different telescopes at the Bell? This telescope, like I want to say all of ours have actually been donated. So, Megan, I don't know if we can point to the telescope. So this Stellaview telescope, and Sarah, feel free to correct me. This was donated to us. Is that correct?
Yes. So very early on, the Bell, we started our telescope programs, and we purchased a few telescopes. But then since then, we've had the generosity of donors help us expand our telescope capacities and different types that we offer. Like earlier, I was talking about refractors versus reflectors. And the Stellarview telescope there that's behind Tad that took our images from tonight is one of them that was donated to us, absolutely.
So, and we've gotten a new one as well. Two new ones that were donated just a couple of months ago. A 102 millimeter refractor, which I've gotten a chance to use, and I absolutely love it. It's a fantastic scope. Apologize, I don't remember the name of the person who donated that. But if you're watching, if you hear this, thank you so much for donating that, as well as donating that 102 millimeter Lunt solar telescope. It's a Lunt hydrogen alpha solar telescope. It's fantastic. I absolutely love it. If we ever get clear skies and see the sun, I will try to take some more. I'll try to get it out. I already got a chance to take some pictures with it. So a huge thank you to everyone who's donated equipment here to help us out. If you can do anything about the clouds, not to get pushy here, but if you can do anything about the clouds too, that's just the next step. And yeah, we have a bunch of different telescopes at the Bell, and weather permitting, we try to use them all. All right, I think for me here and Megan up on the deck. Megan, if you want to say hi.
Hello.
We might need to wrap it up. The breeze keeps blowing, and it's getting very, very cold. I can't feel my lips anymore.
Yes, that is one of the unfortunate things about telescope observing is as the temperatures drop and the nights get colder, there are gorgeous things that come out in our sky and the viewing gets more stable. And so that's kind of a downside or a kind of a not great thing about observing here is the winter skies are gorgeous and they're clear and stable skies, but it is very, very cold for us up on the roof deck. So I know there's so many questions we didn't get to. We are keeping track of all these questions, and they are going to help us inform what we talk about in future star parties. So if you didn't get your question answered tonight, please stay tuned and join us again for our upcoming statewide star party here in November, the week of November 9th through the 14th. We're going to have live telescope viewing every single night during that week of our statewide star party. And then we have our upcoming star parties in December and into 2021 as well. And so all your questions, we do hope that we get to these different topics across all the months. So please, I hope you enjoyed attending tonight, and I hope that you come back and join us for our future months as well. So thank you all. Have a wonderful weekend, and hopefully the clouds will go away soon. Bye, everyone.